For over a century, the power grid's stability was a product of its massive physical scale. Giant, steam-driven iron machines provided the baseline for the entire system. Inside these facilities, rotors weighing hundreds of tons spin at high speeds. This heavy rotating mass creates physical inertia, a mechanical resistance to any change in the grid's electrical frequency. These machines function as a single, unified electromagnetic system. They physically lock the rhythm of the entire grid into one shared heavy momentum. As we transition to wind and solar power, we are removing that heavy iron. Solar panels have no moving parts, and wind turbines use power electronics to connect to the network. The spinning weight that once stabilized the grid is simply gone. By replacing heavy physical machines with lightweight digital electronics, we have created a gap in the grid's natural ability to maintain its own frequency. In modern weak grids that lack this physical stiffness, a minor fault can cause sudden, erratic voltage swings. During these events, renewable energy plants sometimes disconnect unexpectedly. They stop injecting power at the exact moment the system needs it to stay online. Understanding why these plants fail requires a look at the specific control logic governing their inverters. Every solar farm or battery connects to the grid through a device called a Grid Following Inverter, or GFL. The GFL operates under a simple assumption that the grid is an infinitely stable source of voltage. Its only task is to inject current that matches what it sees on the line. On an alternating current grid, voltage constantly oscillates. It's a moving target, cycling dozens of times a second. If the inverter pushes power out of step with this wave, the flow becomes destructive. The two signals must mathematically align to ensure stable energy transfer. Because the inverter lacks a heavy spinning magnet to physically force this synchronization, it relies on a digital tool to track the grid's precise rhythm. That tool is the phase-locked loop, or PLL. The PLL continuously reads voltage at the inverter's terminals, processing that raw data to calculate the grid's exact phase angle in real time. This calculated angle tells the inverter exactly when and how to inject current to stay in perfect sync. It acts as a digital metronome, allowing stationary electronics to perfectly match the power grid. Under normal conditions, this software tracking is highly effective. It is fast, efficient, and replaces the need for massive mechanical hardware. However, the entire system relies on the phase-locked loop's ability to maintain a constant lock on the grid signal. Engineers designed the PLL assuming traditional generators would always be present to provide a strong, clean signal to follow. But during a major grid disturbance, like a lightning strike or a sudden shift in the voltage angle, that signal breaks down. The grid's phase angle begins to jump too rapidly for the tracking software to keep up. As the software tries to calculate this chaotic input, the tracking loop fails. It loses its lock on the grid. Once the PLL fails, the inverter injects current at the wrong angle, which can worsen the instability or force the plant to shut down entirely to prevent damage to its own circuits. This creates a fragility in the system. Grid following devices are incapable of supporting a grid signal that is already broken. To reach a grid powered entirely by renewables, we need a different approach to synchronization. This is where grid forming inverters, or GFM, come in. Instead of passively following the grid using a vulnerable PLL, these inverters act as active voltage sources. They set their own internal voltage and frequency references. By establishing their own stability, these inverters provide the same stiff, reliable foundation that the old mechanical rotors once did, recreating grid inertia entirely through software code.